July 14th, 2005. A spacecraft called Cassini swings within 175 kilometers of Enceladus, a moon of Saturn barely 500 kilometers across, and points a thermometer at the South Pole. The South Pole of a frozen moon should be dead cold. Every model said so. Instead, the instrument came back screaming hot, a scorching patch of heat at the bottom of a world that has no business being warm. Scientists stared at the numbers and reran them, then reran them again, because the readings contradicted every single thing they thought they knew about small, icy moons. The camera was still rolling as the data kept coming back, every packet stranger than the last. But the numbers that shouldn't exist were only the first sign that this little moon was lying about being dead, and the second sign sat waiting in what Voyager sent back from the 1980s. Rewind to the 1960s. In 1789, astronomer William Herschel aimed his telescope at Saturn and found a faint dot, nothing more than a pale speck, drifting beside the planet's rings. He named it Enceladus, and for the next 200 years it stayed a speck. You could sum up everything humanity knew about it by saying it was there. When Voyager finally got a good look in the 1980s, the pictures showed a boring pale marble of ice, its surface pocked with craters, like so many other dead worlds in the outer solar system. It was dismissed as just another cratered corpse, written off without ceremony, and the modern instruments heading to Saturn were looking for a completely different target, and nearly missed this moon entirely. That target was Titan, the giant moon wrapped in a thick orange haze, and the rings themselves. Saturn's ring system, one of the great sights in the solar system, was the main event. The mission cost around $3 billion. Engineers spent years building it, then packed it onto a rocket that left Earth in 1997 for a 7-year journey. Cassini didn't fly straight there. It swung past Venus twice, then Earth, then Jupiter, using each planet's gravity to slingshot itself outward, saving fuel it would need once it actually arrived. In the flight plan, Enceladus earned a few lines and a footnote at best. Nobody cared about the little moon, until one instrument started yelling in a language nobody expected. July 2004. Cassini finally reached Saturn, and after 7 years of waiting, the science team lined up the first close pass of that tiny moon nobody cared about. The images took a while to come down. When they did, people went quiet. Enceladus was smooth, bright, white and smooth, like fresh snow on a parking lot. A world this far out should be scarred with craters, a record of every rock that hit it over 4 billion years. There were almost none. Something had wiped that surface clean, erased the impact history, and whatever did it hadn't finished yet. Craters are the testimony of an old world. This moon looked young, suspiciously young. A smooth face on an old world that should be cratered is weird, but the real alarm doesn't sound for another year. While the cameras sorted through the images, a quieter instrument kept measuring the magnetic field around Saturn, and it kept measuring something wrong. Saturn's field should sweep past Enceladus like wind around a rock. Instead, it bent, kinked, and sagged, as if something were pushing back against it. The magnetometer team had seen this signature before, on one other body in the solar system. A comet. A comet vents ionized gas, and that flowing plasma drags the magnetic field around with it, exactly the distortion Cassini was seeing. If the reading was real, Enceladus wasn't a dead rock at all. It was actively venting something into space, every second, invisibly. The magnetometer pointed a finger at a plume, then the cameras found the cracks. January 2005. Cassini's cameras swept over the South Pole, and there they were, 4 enormous parallel fractures, running like claw marks across the ice, each one wider than a city and stretching for over 100 kilometers. They named them the tiger stripes for how they sliced the surface. But the strangest part wasn't the geometry, it was the heat. The stripes glowed warm against the frozen moon around them, radiating more energy than a dead world should even have stored. Geologists know what parallel cracks on an icy body mean. They mean something underneath is moving, stretching the surface apart, the same way ocean ridges crack apart over a plate boundary. On a world the size of a small country, that's impossible. But a crack is one thing. The next flyby would show what was coming out of the crack, and it didn't make sense for a moon with no atmosphere and no energy budget. Those 4 tiger stripes, named Baghdad, Cairo, Damascus, and Alexandria, weren't just cracks. On the next flyby, they revealed what they were for. Backlit against the sun, the images showed jets of pure water vapor and ice blasting hundreds of miles off a moon only 300 miles wide, a plume so tall it dwarfed the world it came from. It was like watching a comet, except comets burn because sunlight hits them. Enceladus gets almost no sunlight this far out, and it was spraying like it had something to prove. Carolyn Porco called it a heartstopper. Living worlds need an energy source, and the only candidate anyone could think of broke the math completely. That candidate was heat, and in July 2005, Cassini looked for it directly. What it found made the geysers look tame. Enceladus reflects 90% of the light that hits it, and its poles should be the coldest spots on the moon, hovering near 60 to 75 Kelvin. Instead, the South Pole came in at 85 Kelvin, with small pockets soaring past 110. The equator, in full frozen sunlight, was colder than the pole. Scientists put it plainly. It's a hot spot that should not be there. But the heat was just the surface. The real heat source was hiding far deeper, in a place no one had thought to look. Here's what bothered them. All that energy, geysers and heat and liquid water at the South Pole, had to come from somewhere, and every physics model they ran said it couldn't. Radioactive decay in a core that small would have gone cold billions of years ago, and tidal heating from Saturn barely registered, a fraction of what the South Pole was putting out. Something inside Enceladus had to be molten, liquid, or churning, something warm enough to feed those jets. Yet the math insisted nothing that small could still be alive. The only remaining option was something beneath the ice, and confirming it would take years and a trick with gravity. Cassini's first dive through the vapor happened fast, too fast to ask everything at once. Between 2006 and 2008, it kept crossing the South Pole, each visit closer to the actual venting. And every pass added a new contradiction. The plumes were colder than the models wanted, yet they sprayed with more force than those same models allowed. Nothing about this moon was acting like a dead rock. So the mission adapted. It slowed down, did the patient work, mapping, measuring, watching the same jets from a dozen angles over 3 years. Contradictions are how you find something hiding. Each flyby answered a question and raised a bigger one, but the biggest secret of all kept its own schedule. Then Cassini aimed its mass spectrometers straight into the column and let the plume's chemistry hit the instruments. What came back was mostly what anyone expected: water vapor, steam in the freezing dark. But mixed into that water were salts, sodium, chloride, the same ions that give Earth's oceans their bite. Then the organics showed up, carbon chains built by chemistry, not by accident. An ocean that tastes like Earth's, at 1.2 billion kilometers from home. That comparison is not casual. It means the liquid under that ice is not a sterile puddle, it is a working brine. Salt was a massive clue about what sat at the bottom of the ocean, because salt in the plume meant rock down there, and rock with seawater never stays quiet. The salt said something specific. To have that much sodium dissolved in the water, the ocean has to be touching a rocky core, grinding minerals loose the way Earth's deep sea does. And on Earth, rock plus seawater plus heat is a recipe. Hydrothermal vents crackle up from our own ocean floors, and life crowds around them. If Enceladus is running the same chemistry, the moon is no longer just active. It is potentially habitable, not life, not yet. but every ingredient the vents feed on appears to be present. Liquid water, organic carbon, chemical energy leaking out of the rock, all in one place. But potentially habitable is a guess until you can prove the ocean is actually a global ocean and not just a puddle under one pole. Cassini wasn't built to be a scale, but every time it swung past Enceladus between 2010 and 2012, the spacecraft itself became one. The pull of the moon's gravity bends the probe's path by a fraction of a millimeter, and those deviations, tracked from Earth, map the mass hiding below the ice. Engineers expected a fairly lumpy, mostly uniform ball. Instead, the numbers started telling a stranger story. Somewhere under the South Pole, the gravity field dipped, pointing at a region with too little mass, exactly where the surface should be heavier. Tighten the view, and the anomaly got stranger. A region that light, sitting that deep, usually gets crushed out of existence. The math only works if that missing mass is actively held open by something underneath it. The gravity map would reveal a buried ocean bigger than anyone dared predict, and a mass anomaly that still has no clean explanation. When the full map came back, the anomaly wasn't a local dip. It was a signature that only one structure explains: a global ocean, a spherical shell of liquid wrapped around the whole moon, sitting under roughly 20 miles of ice. Here's the part that's hard to sit with. That much water, that deep, should freeze solid in a few million years. The ice above it behaves like a slightly flexible lid, moving in ways that compensate for the mass below. And that motion only makes sense if the sea underneath is liquid, everywhere, all the way around. So the numbers forced the picture. A moon just 314 miles across, holding an ocean that spans its entire interior, on top of a rocky core far from any star's warmth. A global ocean needs a heat engine, and the engine best fits a mechanism that shouldn't work at this moon size. The engine is tidal friction, and it doesn't ask how big you are. Enceladus orbits Saturn on a slightly lopsided, eccentric path, so the pull it feels changes as it travels. Closer in, Saturn yanks harder. Farther out, the grip loosens. The moon flexes with each pass. The interior squeezes and releases, and that constant rhythmic bending grinds against itself, converting motion into heat. The ocean stays liquid because the rock beneath it is being cooked, a slow, steady kneading that has run for billions of years. It shouldn't produce this much heat at this size, yet there it is. The mechanism buys the ocean time, keeps the vents warm, keeps the chemistry alive. Tidal heating explained the ocean, but it was about to be outdone by something the plumes held that no one expected. In 2015, Cassini threaded the plume one more time, and this pass came back deeper, richer, more complete than any before it. The spray was a soup of salts, silicates, organics, each compound a clue about what sat under the ice. The orbiters had spent years reading this water as chemistry. Now the scientists saw it differently. This was the menu of an ecosystem they couldn't see, the grocery list of something alive below the seafloor. The vents were serving food, and the plume was the delivery truck, carrying the inventory up to the surface for anyone patient enough to read it. The plumes had been delivering a message for years, and the message was about to say something about hydrogen none of them saw coming. On October 28, 2015, Cassini made its closest dive yet to the South Pole, just 30 miles above the surface, straight through the heart of the plume. Raw images came back of a landscape fractured and alien, ice torn into ribbons by forces nothing else in the solar system explains. At that range, the surface wasn't a smooth sphere anymore. It was a sheet of cracked glass, ridges and rifts carving through it, like a frozen storm had seized mid-motion. Every frame was territory no spacecraft had ever touched. The instruments drank in the spray as the orbiter swept through, scooping up samples at the closest possible approach. The deepest dive wasn't the last act. It was the setup for the discovery that would crown Enceladus the best hope for life beyond Earth. When the data from that dive got analyzed, one reading stood apart. The mass spectrometer found molecular hydrogen in the plume, the unmistakable product of hot water reacting with fresh rock below. That reaction is one of the simplest ways life can get energy. On Earth, microbes feast on exactly this chemistry, feeding on hydrogen cooked up where seawater meets stone. The seafloor of Enceladus wasn't just warm, it was a kitchen, actively producing food for something. Right now, 75 billion miles from the nearest organic meal we have proof of. One element changed everything, but it also opened a door to a question about that chemistry that the mission couldn't answer. So the mission did the math. Pair the hydrogen flowing off that seafloor with the carbon dioxide Cassini had already measured in the ocean, and the chemical ledger closes. Methanogenesis. A reaction that Earth's archaea run to survive, now running 250 million miles from home. The yield comes out clean. Every gram of hydrogen that hits the right carbon compound returns energy an organism can spend. It's the first calorie count ever done in an alien sea, and the number isn't marginal, it's a living wage. The ocean had food on the table, but a second, far stranger discovery was sitting in the images the whole time, ignored. Back in the imaging team's office, one scientist had been cross-eyeing the same patch of surface in dozens of image pairs, shot years apart. The same crater, the same ridges, the same frozen terrain, lit from every angle. Routine comparison work, until one frame stopped them cold. A dark feature a kilometer wide, riding a surface too bright and too young to carry dark spots at all. And it was reddish-brown, a color that shouldn't survive on freshwater ice here. Ruffled, textured, like a stain that hadn't finished spreading. Then, the tell. Pair 2009 with 2012, and the stain had faded, literally dissolving out of existence, frame by frame, as if it had been drawn in something that could evaporate. A vanishing spot on a bright icy world is either a fresh impact or something rising from below. And the two choices lead in very different directions. First, they tried to write it off. A shadow, maybe, cast by a ridge the lighting kept hiding, so they pulled every viewing geometry they had, and the spot persisted at every sun angle, not a shadow. Resolution next, and topography after that. Blur, a dip in the terrain, a trick of the camera. The ultraviolet data killed those too, because UV sees through surface tricks, and it showed the stain was genuinely dark on the surface itself, physically there. It was real, and it was going. Materials that fade that fast on an airless moon don't sit still, and nothing at that latitude should be replenishing it. With the easy answers gone, the remaining possibilities all point to one unsettling idea about what's happening just under the ice. The reddish-brown cast of that fading spot is the detail that hurts. Ice on Enceladus is white and clean, and dark reds and browns have no business being there unless something from deep below is staining it. And the nearest known source of warm, mineral-laden material is the buried ocean. Not the tidy tiger-stripe vents where we've already looked, but everywhere else, leaking up through a crust that isn't as solid as it pretends to be. Look closer at the slow death of that color. The spot doesn't just get paler, it gets covered, layer by layer, like a wound being dressed. Whatever is underneath is being buried, and something above is doing the burying. The spot fades because something is covering it, and the leading suspects for the covering material bring the story right back to the plumes. On paper, the plume deposits make a clean suspect. Eruptions have been spraying fine ice over this terrain for maybe tens of millions of years, and E-ring particles rain down at a slow, steady rate. Layer enough of that dust over enough time and any dark feature eventually disappears. But the math collapses on its own weight. What we watch the spot lose in brightness would take centuries of plume fallout, maybe longer. The disappearance is happening tens of times faster than any measured deposition rate can explain. Something is covering it with material we never saw arrive. That means active resurfacing, right now, in a place we thought was geologically asleep, and a resurfacing process we can't see leaves a clock we can't read. A spot that vanishes too quickly, an ocean that shouldn't be liquid, a heat source that shouldn't exist. The moon is piling up violations. Step back from the surface, and the strangest part of Enceladus comes into view. Saturn's E-ring, that broad, faint band of haze around the planet, is not some leftover from earlier formation. It is Enceladus, spilling itself outward in a continuous, steady bleed. Every particle in that ring was once part of this moon, launched by the plumes and caught by Saturn's gravity. Enceladus sheds material at the top, and something inside pushes fresh ice up from below to replace what it lost. So the moon is literally tearing itself apart and rebuilding that same crust at the same time, an open system that has kept its own supply line running for millions of years. Very few worlds in this solar system can say that. A moon that rebuilds its own crust is a moon with a surface that is actively lying about its age. Count craters on the northern hemisphere and the story falls apart. Old surfaces are dense with impact scars, baked by billions of years. Up here, the craters are sparse, wiped clean, replaced by fresh ice, so young it carries almost no history at all. This is a hemisphere that has been torn down and rebuilt in geologically recent time. Infrared maps catch the same thing. The north radiates warmth where new material has risen and cooled, a pattern of young terrain that mirrors the active south almost exactly. So the resurfacing is not a southern quirk, it is global, a whole world constantly overturning its own face. Every crater that should mark the Old North is a crater erased, and each erasure is a record of a surface churning from within. The resurfacing points to a churning interior, and within a few years of Cassini's end, new teams would start looking for what else that interior could hide. By 2016, Cassini was out of propellant and living on borrowed margins. Engineers bent the entire mission around one last set of Enceladus flybys, threading the spacecraft through plume and spacecraft geometry just to gather measurements that would never come again. They called it the grand finale. Each pass was a final visit. Each sweep of the magnetometer and each spectrometer readout had to count, because there would be no second chance, no sequel, no follow-up probe waiting in line. The team squeezed science out of a spacecraft already falling. The orbits tightened, the fuel warnings grew louder, and still the team chose to point Cassini at more data, more looks, more time near a moon it had grown to know. One spacecraft, running on fumes, would place its entire legacy on a single question about a moon the size of a country. In November 2016, with the end approaching, Cassini aimed its cameras north one final time. The image that came back showed a landscape fractured and cratered, a pole most of its instruments had studied for a decade. But it was the last time the South would be the first face anyone recognized. For the humans watching from the Deep Space Network, this was a goodbye delivered in photons, a picture of a place nobody on Earth would ever stand on, taken by a machine that would soon be gone, sent across 1.5 billion kilometers just to be seen. That was the final gift of images, or so the team believed. But one camera would capture one more image no one was looking for, and it appears to show something that should not be there. On September 15, 2017, Cassini pointed itself at Saturn's atmosphere and fell. The crash was deliberate. The spacecraft was running low on fuel, and Mission Control refused to risk it ever grazing Enceladus and leaving even a trace of Earth biology in that pristine ocean. So the probe dove, transmitting science until the very last second, then turning into a streak of light over Saturn's cloud tops. Its final radio call carried a single word: goodbye. A made-up word, a signal that had no protocol meaning, sent from a machine that knew what was happening to it. The probe was gone, but its 11 years of data were just beginning to be combed, and the combing would find the contradiction. With the mission over, teams across the planet went back to the archives. Years of observations, most of them never fully looked at, sat waiting for fresh eyes. One set of images had been studied by dozens of scientists and published to acclaim. A graduate researcher pulled them up anyway. What stood out was almost nothing. A faint mark, small and dark, no bigger than a few pixels, present in some frames and fading in others. It sat near a region of the surface that the official papers had never mentioned. The researcher ran the numbers once, then twice. The object appeared to be moving, slowly, across a moon where nothing was supposed to move. What the researcher found in the archive was small, dark, and fading, and it would drag the whole field back to a question everyone thought was closed. To test that question, a lab built a version of Enceladus in miniature. A chamber chilled to -190 degrees Celsius, a slab of ice spiked with the same salts the plume had sprayed, and a particle gun firing Saturn's radiation at it for weeks. When the team finally analyzed the ice surface, the results rewrote the story. Many of the chemicals the mission had celebrated as fingerprints of a living ocean, including hydrogen and other organics, could be produced right there on the ice by the radiation alone. No sea required, no biology required. The lab result cast doubt on half the mission's biggest claims and proved that a place can look alive and be completely dead. The lab had just argued that radiation alone could fake the whole story, but the ocean answered back. Cassini measured heat pouring out of the South Pole at roughly 15.8 gigawatts, 10 times what radiogenic decay and tidal flexing together could ever produce. Somewhere below, something warm was working. Then the plume gave up hydrogen, and it wasn't the random kind. That gas is the signature of seawater reacting with hot rock, a process called serpentinization, cooking a chemical kitchen on the seafloor. Here on Earth, the same reaction feeds entire ecosystems that never see sunlight. And then there was the wobble. Cassini tracked Enceladus's libration for years, pinning 5,800 surface features by hand across hundreds of images. The moon swayed 1/10 of a degree as it orbited Saturn, and that sway was only possible if the ice shell floated free, nothing solid tying crust to core, a global ocean. The water survived the challenge, which forced the hardest question of all. If the ocean is real, where is everyone? Think about what that ocean offers. In the deepest, darkest water on Earth, microbes cluster around hydrothermal vents and harvest energy from hydrogen and carbon dioxide, turning them into methane. It's one of the oldest tricks life has, and it needs nothing from the sun. Enceladus might outdo those vents. Its young rocky core reacts with clean water, and models suggest it generates bioavailable energy at concentrations some researchers call a candy store for microbes. Methanogens there could work harder than any on Earth. The estimates get quietly staggering. One study put cell densities near the vents at around 1 billion per cubic centimeter, and suggested that a single fly-through of the plume could sweep up thousands of microbes. If life were there, it wouldn't be hiding, it would be everywhere. But imagining the life was easy. Detecting it from orbit turned out to be the cruelest part of the whole pursuit. Here's where the whole campaign started to crack. The plume was the obvious way to sample the ocean without drilling, but Cassini's mass spectrometer couldn't say whether the molecules it caught had risen from the deep or been stripped off the icy crust. Both look identical on the detector. It's a contamination bind. Radiation sweeps the surface and coats it with material that has nothing to do with the ocean, yet it all lands in the same plume. The instrument measured everything at once: deep water, surface frost, debris, all mixed, all readable, none separable. Separating them takes a craft built for the job, one that could fingerprint every molecule back to its source. Missions like that were proposed again and again. An Enceladus explorer, a life finder, a lander with a heated drill. One by one, they were shelved. The one instrument that could have told the difference was the one mission that never launched. You might think Cassini's ending was about fuel, a spacecraft spent beyond its years. It was about something quieter, The probe was still working perfectly, and the team deliberately flew it into Saturn anyway, because a dead Cassini adrift could one day tumble onto Enceladus. And Cassini never got sterilized to the standard a habitable ocean demands. The numbers behind planetary protection are stark. A Mars lander can carry no more than 300,000 spores. A lander bound for a special region, where organisms might actually grow, is allowed just 30. For Europa, the standard is passed as odds, the chance of contaminating its ocean held to less than 1 in 10,000. Every mission bets those numbers. That's the trouble with reaching for another world. Every gram of hull carries dormant Earth bacteria, and space station experiments prove some can endure the entire flight. Fly a probe into the plume, and you might finally read that ocean, but you'd never be sure the life you found wasn't the life you carried. Every plan for returning to the moon collides with the same wall. We cannot touch it without risking destroying what we went there to find. Read it from the other side and the ledger flips. Every year Enceladus stays untouched is a year its ocean keeps its secrets, its vents still firing, its molecules still streaming past, and no one reading them. That silence is the real cost, and it's paid in questions that never get answered. There's a tragedy wound through all this caution. Cassini spent its last drop of fuel to keep that water clean, and the clean water is precisely what no machine now samples. The most life-friendly ocean we know sits pristine, unread, protected from us, and therefore from knowing. Missions run on budgets, and budgets choose winners. In the rounds where an Enceladus probe could have flown, the money went to Mars, to Europa Clipper, to already crowded schedules. Launch windows keep ticking past, and with each one the moon stays a little further away from the one answer it could give. Yet waiting may be the only option, because the design of the perfect Enceladus probe was finished years ago. It was locked in a drawer. It had a name, a team, and instruments worth building. The Enceladus Life Finder would have orbited Saturn and flown through the plume 8 to 10 times over 3 years, sniffing for amino acids, fatty acids, and methane with 2 next-generation mass spectrometers. It was proposed in 2015 for a discovery slot, drew a star roster, and died on the selection floor. So they tried again. In 2017, the same core concept went before New Frontiers, the bigger flagship caliber budget, and once more it did not make the cut. Another concept, named Life, would have flown through the plume, caught the grains, and brought them home to Earth, the cleanest possible answer to the contamination riddle. It, too, was shelved before any hardware existed. None of these were bad ideas. They were the good ideas that lost. The paper studies are thick, the team still eager, the launch windows still open. All that's missing is a slot, a budget line, a selection letter that never comes. One proposal came closer than any other to flying, and its cancellation echoes through every discovery since. So the flags go up again. NASA's Enceladus Orbilander would swing in close orbit before dropping a lander through the plume to sniff the venting directly. ESA's Enceladus Explorer sketches an even bolder shape, a probe built around surviving the radiation long enough to measure what matters. And then there's the plan out of China, an orbiter, a lander, and a drill all riding together, engineered to bore past the ice and reach the ocean itself. Not to taste the plume, but to break the surface and sample the water underneath, the first hardware ever pointed at that boundary. Every proposal is a bet placed years in advance on a world 790 million miles away. Every one of those missions depends on one thing no spacecraft can provide yet: a way to know what the ocean hides without contaminating it. But the ocean has never needed a probe to start giving things away. At the bottom, tidal kneading of the moon's core should press heat into the seafloor, a warmth measurable in the way water rises and turns over. In the plume above, nanograins of silica drift up from that deep floor, each one carrying a memory of its birthplace. Salinity gradients sketch broad currents. Chemical fingerprints in the sampled grains map where vents cluster and where they stay quiet. It is cartography drawn entirely in proxy, a chart of a world we have never once laid eyes on. Everything scientists know about the ocean's bottom was inferred from grains that flew through a single instrument, and those grains have more to say. Because the silica isn't just present, it's picky. The grains in the plume are tiny, only a few nanometers across, and their crystal structure is exact. That precise size and that specific shape can't form by chance. They only crystallize the way they do when hot water meets fresh rock, the way steam vents do on Earth's own seafloor at temperatures near 90 degrees Celsius. Each grain is a record of that collision, preserved mid-flight and delivered to an instrument 400 million miles away. It's a fingerprint of vents that no eye has confirmed. The silica grains led to another contradiction. The temperatures they imply run hotter than the models say the moon's engine can deliver. Here's where the numbers stop adding up. Cassini measured the heat radiating off Enceladus's south pole, and the total is roughly twice what tidal squeezing can supply. The moon gets bent by Saturn's gravity as it orbits, and that flexing should generate power like a bent paperclip warming in your hand. It simply isn't enough. Researchers have spent years trying to close that gap with tweaks to the orbit, the ice shell's thickness, the way the interior bounces. Every adjustment shaves off a fraction of the missing energy, and every one falls short of what the instruments see. The moon is burning more energy than it could plausibly earn, and the only unwritten solution is something beneath it we haven't named. So the proposals arrived one by one. A young radioactive core, still hot from formation, could be adding its own contribution. Ammonia in the ocean would lower the freezing point and change how convection churns the water, letting it move heat upward more efficiently. Each idea used the physics we already understand, applied harder.
None of them were wrong, exactly. They just described mechanisms that were plausible without being proven, placeholders for a balance sheet that refused to close. Fresh ideas for the missing heat poured in, but one researcher followed a stranger trail into the oldest and least examined part of the whole record.
Somewhere in the archives sat images from Voyager, two spacecraft that swept past Saturn in the early 1980s. Their cameras were primitive by today's standards, grainy and low resolution, but they caught Enceladus's surface in a way no later mission would. Cassini would photograph the same region in the 2000s. That 40-year gap was the point. If the surface had changed between those two visits, the difference would be proof of something active, something shifting under the ice. Set the old frames beside the new ones, and the comparison hummed with possibility. The old images contained a feature that the new era had missed, and comparing them took the shouldn't-be-there anomaly and made it worse.
So the spot wasn't merely fading by the time Cassini looked, it had already been gone for a while. The Voyager frames had recorded it decades before anyone thought to check.
Laid side by side, the math said the dark feature had vanished between the two visits on a clock nobody had suspected. The images had held the evidence far longer than the instruments had held the attention. The erasure was silent, patient, and complete before the first scientist ever asked about it. Whatever erased the spot has been at work for decades, and the record suggests it might have company. Running the same subtraction over the full map turned up a second irregularity, smaller and quieter, sitting in the northern hemisphere, reddish-brown where the first had been dark, and dissolving at a slightly different pace. It shared the first spot's signature, the same slow burial, the same refusal to show its maker. Two anomalies now, in different skies, wearing different colors. A lone dark mark could be dismissed as a trick of light or a flaw in an old sensor. Two dark spots dissolving on a bright moon is evidence of a process, and a process, once identified, can be watched.
The spots' positions, their colors, the order in which they vanished, they pointed one direction. Something was falling from above, a thin rain landing across the entire globe and slowly burying whatever sat beneath.
The source traced back to the plume itself, ocean spray launched from the South Pole, carried by currents all the way around the world before settling. The models said such fallout should stay regional, pooling near the vent. The images said otherwise, thicker and faster than any simulation permitted. A global rain of ocean spray crisscrossing the whole world. The implications for where ocean life chemicals end up are about to get strange.
Flip the model around and everything inverts. If spray can fall anywhere on the globe, then everywhere is a sample. Every square centimetre of ice has been caught mid-freeze, holding a snapshot of whatever the vents were releasing at that moment.
That's not contamination anymore. That's a record. A snowfield laid down at kilometers per second across the entire moon, layer after layer, each one tagged by where it sat and when it landed.
Look close and you can almost read it like sediment. The deep troughs preserve the older falls. The smooth plains show the newest coats. The whole surface is a depositional history no one had thought to count as data. If the surface is a frozen archive of the ocean, then 2 decades of images are a library of the sea's changing chemistry, one we've barely opened.
Here's what that could unlock. Shoot the same patch of tiger stripe again a year later, and the new frost tells you what the ocean was doing in between. Vent chemistry, salinity shifts, maybe the pulse of a current. Same ground, different date, a before and after of a hidden sea. Pluto's geology changed our reading of the outer solar system in a single flyby. This is that, but with a timestamp attached to every grain. The only catch is repetition. Climb the archive, catalog the frames, and the archive becomes an instrument. Without a plan to re-photograph the same targets over years, though, the library stays a pile of pretty pictures with the volumes unread. But reading that archive demands that missions photograph the same place again and again, and a budget crisis was about to decide whether that ever happens. Here's the raw math of deep space. An Enceladus flagship with the full instrument suite runs into the billions, and billion-dollar flagships are the first thing a strained budget eats. One got cancelled outright. Another slid a decade to the right. A third was redesigned so many times the final version flew with most of its payload stripped out. Every one of those cuts landed on the same choice: buy a few more years of observation or let a dozen promising measurements die on the drawing board. The science community didn't take it lying down. They went hunting for a cheaper path, and somewhere between a survivable price tag and a plausible launch window, they found one. Out of that chasm came a plan so cheap it almost worked, and so slim it almost flew without any of the science. A private backer picked up the tab NASA wouldn't touch, and the pitch was almost defiant in its simplicity. A small spacecraft, mostly a mass spectrometer with a ticket to Saturn, launched wide open on an affordable rocket. No orbit, no landing, no spare pass. One shot through the geyser field, one readout, and it keeps going. It would flash through the spray at several kilometers per second, tasting a body of water no flagship had ever priced below $5 billion. The canary, in other words, sent into the mine. If that hidden sea held anything odd, the cheap shot would smell it on the first sip, or not at all. Engineers even liked the irony of it. A mission lean enough to fit a single billionaire's checkbook, flying a decade before any flagship could. And yet the whole architecture balanced on that one pass, that one instrument, that one hope. The cheap shot's single measurement was designed to answer the one question everything else hinged on, and it was never taken. That measurement goes straight to the heart of what the plume actually hides. Cassini spent years tasting the spray, but the spray is a menu, not the kitchen. Every drop it caught had already been frozen, launched, and stripped by vacuum. The ocean itself, sitting under roughly 30 kilometers of ice, has never been sampled directly. No instrument has ever been lowered into that water, and no probe has ever held a beaker of it up to the light and asked what's actually alive in there. We know the place runs warm, we know it runs salty, we know chemistry that shouldn't coexist is happening on the seafloor. We have never once checked whether anything is driving it. That's the gap the campaigns keep stacking missions against, and it stays empty. The answers keep leaking out sideways, in nanograins, in acidity, in the wobble of the moon's core. Every one of them a photograph of the crime scene, none of them the witness. That measurement is the cliff the campaign has been building toward. No probe has ever gotten close to making it. So why should this matter past the headlines? Because Enceladus is the closest thing to a laboratory the solar system has left. A global ocean under 20 miles of ice, warmed by chemistry we didn't expect, spraying its interior into space like a deliberate offering. Every ingredient for life as we know it shows up in that spray: water and energy and carbon, the whole recipe. Cassini died on purpose to protect it, plunging into Saturn rather than risk contaminating the one ocean that might hold a second Genesis. That single gesture tells you where the biggest question in science has been circling for years. We keep designing spacecraft to reach a place no robot has touched, at a cost we keep talking ourselves out of. And still the moon waits, small, bright, serenely pumping a hidden sea out into the dark, the nearest ocean beyond Earth, and the best shot we will ever get at an answer we can actually test. Enceladus isn't just a mystery, it's the single most testable place in the solar system for the question of whether we're alone. Look back at the whole arc for a second. A hotspot that thermodynamics says shouldn't exist, glowing in a moon cold enough to freeze nitrogen solid. An ocean that should have crystallized to bedrock 4.5 billion years ago, still liquid. A spot that faded from frame to frame when nothing in the ice should ever change that fast. And food in the plume, organic molecules that nobody expected to find riding the spray. Each one is a rule broken, a neat explanation that dies on contact. But they're not separate mysteries, they're symptoms of one thing we can name but not explain. One engine running under miles of ice, and we've left it running while we watch from a desk. Every month that screen is dark, another piece of that signal cools into the ordinary. The real question isn't whether something is alive in that dark sea. It's whether we'll ever be brave enough to go look before the evidence fades away. Months after the final flyby, a junior scientist is clearing out a drive that nobody wants to touch. On it, a stack of telemetered images no one ever processed, frames transmitted in compressed bursts in the days before the end. These are the last shots Cassini took from the darkest side of the plume, the side that faced away from every instrument tuned to look. Cheap frames, low priority, tagged for later. Later never came, until now. They get pushed through the pipeline one by one, mostly noise, mostly nothing. Then one frame stops the room. The temperature model says it should read near 50 Kelvin, and the data disagrees by a margin wide enough to mean the model is wrong, or the moon is. One of those frames doesn't match the temperature model, and it was taken weeks before the plunge, not during it.
Here's the strange part. That frame was flagged for senior review, and it never moved. A routing error, a misguided destination, an inbox that filled and swallowed it. The detail hardly matters.
It sat in a queue while scientists argued about budgets and priorities, about whether a return mission was worth the cost. All the while, the only frame that might settle it was parked behind a door nobody thought to open.
Sit with the arithmetic for a second. One file transfer mistake, one wrong digit in an address field, and an entire discovery nearly evaporates without a trace. It would have been filed as a cleanup item and gone.
But here's the thing about that routing error. It wasn't the only one of its kind. The first routing error got all the attention. It should have. But digging through the same instrument's archive turned up a second set of files, logged under a different mission identifier entirely, one that had nothing to do with Enceladus. Those frames sat in that mislabeled folder for years, retrievable technically, but only if you already knew the identifier, only if you already suspected what you were hunting for. A search engine can't find what you don't name. The two errors share a signature. Both were one-field mistakes. Both buried data that contradicted the tidy summary. And both were logged by people who would have had no reason to log them wrong on purpose. Accidental, 3 times over, is a pattern. So the question becomes, who else already knew and had reasons to keep looking?
That's when someone found the notebook, a design phase binder from 2005, before the spacecraft ever reached Saturn, before a single frame of Enceladus existed. And inside it, one engineer had written a name for a feature no one had seen.
Stray light corridor. It was flagged as a detector artifact, written off as the instrument scattering light off its own housing, a known failure mode. The notebook says they expected it to pollute a thin band of pixels and nothing more. But the notebook also did something odd. It drew a boundary around that corridor on a map of Enceladus's south pole. Engineers date the annotation to the same week the design review stamped the instrument flight ready.
Nobody read it twice. It was a caution note, a procedural footnote. Except the buried frames, the ones under the wrong identifier, they load up clean. That stray light corridor shows up in them with a shape the notebook never predicted.
Because the ghost is not a smear, not a streak, not the soft blur of a lens flare bleeding across a row of pixels. At full resolution, it resolves into something else entirely.
A discrete feature, roughly circular, sitting dead center in a region the team had already mapped as an active vent field. It's cold, colder than the surface around it. Cold in a place where the vents are pushing out 200 degrees Fahrenheit warmth.
A circular cold patch surrounded by active vents. On Enceladus, that's backwards. Every model says that geometry shouldn't hold heat away from itself, not in open terrain, not for the years these frames suggest. It is the first concrete description, and it came from files nobody was supposed to open, and its edge, at full resolution, is not smooth, it is serrated. Pull that edge up, and the serration is not random noise. The spacing, the angle, the way each notch leans forward, it matches a surface morphology catalogued once before on a body 4 billion kilometers away. On that other world, the pattern forms where layered material is undercut, then collapses in sheets. The archive drawer holding the comparison frames from this hemisphere, the exact ones that would settle it, has a spot where a frame should sit.
Keep that missing frame in mind. That missing frame, however, has a twin, and the twin lives in a public outreach archive.
The outreach copy was released for schools, for press kits, and it is lower resolution, but it is complete, every frame present, where the science archive has gaps. And it shows the serrated feature from a second angle, offset roughly 40 degrees, looking across the structure instead of straight down. The notches are still there, in the same places, casting the same shadows. Clean detector artifacts do not survive a change of viewpoint. Real geometry does.
Neither image was ever annotated, catalogued, or discussed in any published paper. But compare the two, and the feature has height, thickness, actual volume, sitting inside the ice. Real volume that the only instrument capable of imaging it at depth had already been deliberately pointed away from.
The commanding history makes it plain. 2 observation windows, logged months in advance, had their targets directly over that buried feature. Ideal geometry, camera nearly vertical. Both were cancelled. In their place, the instrument was retargeted to the opposite hemisphere, featureless planes already imaged twice before, and the log entry for the swap carries a single label: housekeeping. Housekeeping does not usually require an instrument that images 30 meters below the surface to spend its only available passes staring at ground it has already seen. The reason given for the change is 1 sentence long, and that sentence does not survive contact with the flight log. The sentence reads, in full, housekeeping. One word where the flight log ought to say what happened and why and to what end. But the commands went up hours earlier, sequenced, deliberate. Someone had to compose them, check them, approve them. That someone wrote down a reason the sequence itself contradicts. The anomaly is not in the instrument. The anomaly is in the documentation, a small tear where the paper stops matching the flight. Which raises an uncomfortable possibility that the change was made by someone who didn't want the feature seen again. Give the mundane explanation its due. A tired scheduler, an honest mislabel, a bad day on shift, a form filled out on autopilot. These things happen. They happen all the time, actually. Let that version fight the evidence. Strain against the sequence, the timing, the deliberate rerouting of scarce passes. A tired person makes one mistake. This was a series of choices. It loses on one date. The same mislabel appears twice, 11 months apart, in two different hands. Two entries. Same word, same slot in the log, written by people a year apart. That is not a blunder, that is a habit, and routing systems do not develop habits. People do. A habit is a decision repeated until it stops being a decision. It wears a groove. By the second time, the hand did not even think about it. And people, in this story, have always left a trail. The next trail runs through a phone call logged 2 days after the final flyby. December 21, 2015. 2 days after Cassini's last brush with Enceladus, and the mission's personal communication log shows one observations planner reaching out to a colleague by phone. Nothing unusual there, except for what the call was about. Its subject line carried the feature's coordinates, exact to the arcsecond. The same numbers that had been quietly forwarded, transcribed, and buried across 3 previous sections of this story. On paper, it reads like routine follow-up work. But routine follow-up gets CC'd to a shared drive. This call was placed to a personal number, logged off hours, and marked for no distribution. Someone wanted a second opinion, badly enough to reach around whatever channel was supposed to exist. That colleague's reply is not in the archive, but its absence is its own kind of evidence. So we went looking for the reply, every backup the institution kept, every mirrored mailbox and nightly tape, every archived thread from that month. Searched by sender, by date, by those coordinates. Nothing. The message was either never sent or it was destroyed within the window the backups ought to have preserved. 2 ways to read that, and both of them lead to the same cold fact. The thread goes silent at the exact moment it mattered most. Not a denial, not a cautionary note, not even a placeholder, just a gap where a conversation should be. In 11 years of mission records, it is the single cleanest absence we have found. Cold threads, though, are where this story keeps resurrecting, and resurrection has a price. One reading of these gaps is that the filmmakers target 3 figures whose careers genuinely bent after 2016. The record suggests one of the planners who flagged the coordinates was moved off the team's core imaging work in early 2016. Not fired, not reprimanded, not accused of anything, just reassigned, defunded, and eventually dropped. The polite machinery of a career closing down without a single door being slammed. Another scientist connected to the same thread saw a planned review article shelved. A study section flagged it as duplicative. One by one, the people who asked the obvious questions found their next steps had gently disappeared. And the quietest cost of all was to the one question nobody was allowed to ask out loud. So here it is, the question nobody was allowed to say out loud. If the feature in those images is what the data keeps suggesting, then the ocean beneath Enceladus has been mismodeled for a decade. Every published conclusion, the plume chemistry, the heat budget, the tidal flexing numbers, sits on a floor that may not be the floor at all. Consider what that means. A global ocean model is a single continuous picture, one pressure gradient all the way down. The imagery shows a structure that should not generate those heat signatures, should not bend the libration readouts the way they bend. 10 years of peer-reviewed work assumed one smooth lower boundary, and this feature cracks it wide open. Nothing about this is easy to say, because nothing observed from Cassini ever directly touched that boundary. It was inferred. Every temperature, every density, every geyser timing climbed out of a model built on a guess.
The wrong floor, though, is only wrong if the feature is real, and that brings us back to the one test nobody could run.
Yet a door does exist, even if nobody behind it will open it. The Planetary Science Decadal Survey, the community's official roadmap through 2032, ranked an Enceladus flagship as its second highest priority, an orbiter and lander fused into one craft, the Orbilander, built specifically to get under that ice.
Here is what the design actually calls for. A November 2038 launch, a 7.5-year cruise to Saturn, then a 2-year stay parked on the ice. It would sample the plume 12 times from 31 miles out, and from orbit it would read the boundary that Cassini could only infer.
That is hope with fine print. The mission has not been formally approved, and no launch date is locked. It lives in design limbo, half-funded, and even on schedule, it does not reach Enceladus until the mid-2040s. That is a long silence for a question this loud. Half-funded, maybe, but a rival mission is fully funded, and it carries an instrument that could image the feature from orbit without landing. Meet the rival. Europa Clipper left Earth on October 14, 2024, an orbiter funded, built, and already in flight, a spacecraft that took NASA years and billions to finish. It was never written for Enceladus. Its flight script is Jupiter's moon Europa, 49 flybys over 4 years. Yet read its instrument card and the tension starts. The ultraviolet spectrograph, the high-resolution imaging system, the thermal emission mapper that sees heat at meter scale, the radar that sounds the ice from orbit, and MISE, the mapping imaging spectrometer for Europa, a near-infrared eye sampling, 800 to 5,000 nanometers in 10 nanometer slices. Now the catch. That near-infrared window is not tuned for Europa alone. It overlaps the exact wavelength band where the Enceladus feature leaves its signature, the same band Cassini swept past for 13 years carrying filters that could not see it clearly. And the mapping camera rides a gimbal, able to swing its eye nearly 30 degrees off the Europa track. That sensor, as it happens, was built by the same laboratory that built the housekeeping camera.
So we went back and listed the names, one by one. The engineers who ran the ground tests in the hangar, who watched that sensor misbehave under a blackout shroud, they are the same names now attached to the Europa instrument leads. Same lab, same badge numbers, same coffee rooms, 20 years apart.
And across both lists, one name appears twice, in a senior role. The person who signed off on the old components acceptance paperwork holds the senior position on the new mission's science team. That name is everywhere in the archives, and nowhere near the interviews.
That name has never once spoken about Enceladus in public, not in a single interview, in 20 years.
So we catalogued the public record. It is a clean, flat line. No papers, no conference talks, no quoted paragraph in a single press release. 20 years is a long run of nothing, and the nothing sits right on top of the one world this person helped write the observation plan for. The plan named specific bands, specific exposure times, the exact geometry to catch a faint plume against open space. It is arguably the most detailed description of Enceladus ever produced by that team, and its author has spent 2 decades not once saying the moon's name aloud. That takes work. A 20-year gap like that does not happen by accident. It happens by discipline. But silence is not absence, and the person's private papers are now public record. The archive arrived in a long run of bankers' boxes, bequeathed to the university library. Most of it is mundane, travel receipts, old letters, draft slides. But in box 11, folded inside a program for a 2006 conference, we found a margin note that stopped us cold. The conference agenda had a short session on outer planet moons, 5 talks on a Tuesday afternoon. Someone had circled one line in pencil, and next to it, in the careful handwriting we had come to recognize from decades of memos, were the only words about the subject that ever came from that name. The note is 2 words, and those 2 words change what we think the entire program believed. The 2 words were avoid region, not a question, not a hypothesis, a note of warning, written in pencil, years before any instrument ever returned an image of the feature. Someone on that program knew about it before the cameras did. Set the date against the observation logs, and it becomes stranger. The handwriting predates the first clear detection by half a decade. That means the knowledge was not assembled from data, because the data did not exist yet. It had to come from somewhere else entirely. Whatever the margin note was answering to, it was specific. It named a corridor of sky, not a vague concern. A private suspicion, committed to paper, then left to sit in an archive while the rest of the program went on pretending. Which means the feature was not discovered late, it was avoided early. Avoided early and systematically. Go back through the 2006 observing plan with the note in hand and the pattern snaps into focus. It was never one blocked window, one unlucky geometry. It was entire corridors, steered wide of the region, across 6 separate campaigns in a single cycle. Each plan on its own reads as innocent, a slight shift in pointing here, a different phase angle there. Nothing a reviewer would flag. But laid edge to edge, the adjustments all bend the same way, like 6 photographs of the same road taken a second apart. No single engineer is likely to have made all 6 calls. That kind of consistency requires coordination, which requires a conversation, which leaves no trace in the public packet. The plans only show the result. 6 campaigns is more than a habit, it is a policy, and policies have owners. So we went looking for the owner. The public archive holds hundreds of pages on Enceladus mission planning, yet only one internal memo even uses the word policy for observing geometry. 1. And that single document is redacted in exactly the region of interest. Not redacted in the messy way of a hasty legal scrub, redacted with care, segment by segment, each gap precisely sized, as if the person who filed it knew exactly which coordinates mattered and wanted no one to read them again. Redaction, in a NASA adjacent archive, is itself a fingerprint. A document only gets that treatment when someone above the author decided the words had to disappear. And that fingerprint, run forward through the funding records, leads somewhere specific. It leads to a funding line. That code on the marked memo doesn't file into some neutral budget line. It resolves to a single item, one line in the ledger, the kind of line that normally dies in committee. A proposed ocean sampling experiment, an instrument designed to fly straight through Enceladus's plumes and taste the subsurface water directly, was put forward for selection. It wasn't chosen. The proposal lost out on the merits, or so the record would have you believe. Too much cost, too much risk, a science return that didn't clear the bar. The paperwork closed, and the team folded back into the larger program. But funded work leaves a paper trail, and that trail kept one thing alive, a single prototype that kept its testing budget hidden inside another heading. Same lab, same serial tags, a different name on the door. Read the funding records and the engineering logs side by side, and the rejection letter starts to read like a cover story with a timestamp, not a decision. The experiment was never selected. Its technology was quietly tested anyway, in full, on Enceladus's own plume.
Here is where the story turns quiet. October 28, 2015. Cassini swept through Enceladus's south polar plumes on the deepest pass any spacecraft ever made, diving to 49 kilometers. That was the E-21 encounter, and the spacecraft crossed the plume in seconds, moving faster than 19,000 miles an hour.
Now watch the sampling method, because it matches the shelved experiment's prototype down to the last engineering choice. No landing, no drill, no excavation. The unselected design counted on the spacecraft's own velocity to do the work, ramming plume material into the analyzer at full speed along a single line of flight. Cassini used exactly that approach in 2015, one fast cut through the densest core of the plume, in and out before the jets could change. So every molecule that came home was gathered from that one altitude band. The layer, the trajectory happened to cross. Every plotted result in the published papers traces back to that single depth. A sliver, not a survey. Exactly one depth. And the feature of interest sits at a different depth, entirely unsampled. So sit with what a single depth means. Everything the mission ever tasted, every grain, every vapor trace, every published snapshot of Enceladus's chemistry came from the layers above the feature's horizon. The boundary the whole pursuit was aimed at sat below the sampling line, out of reach. Every instrument on that flyby looked up at it from the wrong side.
What streamed up through the plume had already been passed through every layer above, sieved and researed by altitude as it escaped. Any molecule that survived told you about the climb, not the source. Reading the plume for the ocean is reading the ocean through curtains you cannot see.
So the entire chemical record could be one long, filtered story, and nothing in the data would expose it, because the instruments were never positioned to check. The filter did its work before a single spectrometer ever switched on, every reading arriving at the instrument already shaped. If the story is filtered, then the hydrogen signal that once thrilled the world was filtered too. So run the famous 2017 announcement through that filter. Cassini's deepest plume dive, 48 kilometers up, returned a plume that was 98% water, 1% hydrogen, the rest carbon dioxide, methane, ammonia. The team behind it drew the optimistic line: hydrothermal vents on the seafloor, serpentinization, microbes with a food source. But the depth filter reshapes that story before it starts. A reading that arrives at the inlet already altered is not a measurement of the ocean, it is a measurement of the vent's own chemistry, the chemistry of the rock wall that shaped every molecule on its way up. The hydrogen signal that once made headlines, that NASA called the closest we have come to a habitable place, may have been telling us something narrower and colder all along. Not that something eats here, but that something cooked here. And if it is vent chemistry, then the food source conclusion never was a conclusion at all.
Look closer at the original paper, and the hedging is already written into it. The same scientists who said the conditions for habitability were nailed down also wrote in the same release that this does not tell us whether life is there or not.
They conceded the process could be something else entirely, something only reproduced in a lab. They admitted the instrument itself had generated spurious hydrogen in earlier passes, water reacting with its own titanium parts, a bias they hoped they had accounted for. How many assertions about habitability survive contact with an ocean nobody has ever sampled? Every one of them rests on a depth nobody reached and a story nobody verified. The papers hedge, the press releases soften, the word may does a lot of carrying. Across the table from that hedging sits one document that hedges nothing, a 2018 engineering failure review, classified. Classified does not mean invisible. This review has a public stub, the bare bones that any agency file keeps, a title, a date in 2018, a classification code, and almost nothing else. Failure reviews exist for a reason. When a component fails, you document it, you find out why, you make sure it never happens again. That is routine engineering, and routine engineering does not get classified. The very existence of a sealed review says the failure, or the near failure, or the concern that never quite became a failure, mattered enough that the public summary was filed away behind a code. It says the mission's real risks were kept somewhere the press could not read them. So you check the stub for one detail, the only detail it gives freely, and you feel the drop in the room. The review's subject line names a component that never once failed in flight. That's what makes it strange.
So you pull the components file, flight after flight, the same column, the same 4 letters. No failures, no anomalies, no service advisories filed against it ever.
Not one discrepancy logged across every mission that carried it. The thing was boring in the way hardware is supposed to be boring. Quiet, reliable, unremarkable. Which makes the classified review of it genuinely strange. You do not convene a failure review of a part that has never failed, and you do not classify its findings to protect a success. So the review was about something else, And component was the label. The question is, label for what? 2 years later, a single page is declassified. One sheet, heavily redacted, most of it blacked out, and it renames the entire review. Downlink prioritization, it says, a bureaucratic mouthful that quietly describes a simple thing: which data got sent home and which data stayed behind on the probe. Every gram of the science budget had been spent on gathering that data. The choice of what went down and what never did was the last decision, and it was made, not discovered. Sent home and did not is not a technical failure, it is a choice, and choices have authors.
The review has a signature, and it belongs to a junior scientist you met in the very first minutes of this film. The one who asked the question, then asked it again, then watched the room go still.
In the months after, their name vanished from mission memos, then from team lists, then from the field entirely, and for a while, the record just went quiet about them. It was not a scandal with a single blow, it was one question too many, answered with a closed door, then another door, and the slow freeze-out that never leaves a paper trail. That scientist has since left the field entirely and left behind a personal data drive with the only unredacted copy of their findings. That drive sits in a drawer somewhere, unplugged, unopened in years. Its owner made a point of storing it off-site, away from the institution, away from the network, and never once connected it to a machine that could call home. The only thing keeping those findings out of the public record is a single document, signed in an office that no longer exists. A non-disclosure agreement, drafted to cover a project that outlived its own paperwork.
Enforcement was never the point of the thing. The point was the chill it put on anyone who touched the material. The sense that asking for clearance meant asking for trouble. And the owner honored it long past the moment it stopped applying.
An NDA with no surviving signatory on the agency side since the enforcing office was disbanded years ago.
So here is the legal knot. A contract is a meeting of two parties, and one of those parties is now a corpse, the other a closed office with no forwarding address. Who enforces a promise when neither side can be found to keep it?
The answer turns on inheritance of all things. When an office is dissolved, its agreements pass to whoever inherits its functions, and when a person dies, their obligations pass to their estate. Both chains of custody sit so tangled that a court would have to decide which ghost owns the signature. No one has asked that question in public, not yet, but the law has a default for a contract with no living party on either end. It simply stops being a contract. Inheritance, it turns out, is the exact legal mechanism that also governs what happens to Cassini's raw data after the parent agency's retention period ends. Here is the part that changes the timeline. Raw mission data does not belong to the public forever. It belongs to an archive, and an archive has a retention clock. Count the years from collection, add the standard term, and the whole dataset matures at once. That maturation date falls inside the current decade, not far off, not in some vague future administration, but on a fixed calendar day when the archive's obligation ends and everything it holds passes into the public domain, redactions included. Every scrubbed frame, every withheld spectrum, every footnote that the NDA was meant to keep buried. On that day, the redaction filter switches off, and the label that now marks dozens of files as sensitive becomes a historical artifact in its own right. That fixed day is closer than most people in this story want it to be. Map everyone in this story against that fixed day, and the picture sharpens fast. People who hold the data lose the most when it comes out. People who signed the NDA have the most to gain from the redaction filter staying on a little longer and losing the most if it never switches off. So it's worth asking who left before any of that had to be resolved. Not fired, not forced out, quietly retired with a full pension and a clean clearance, just ahead of the moment the paperwork would have made them answer a direct question. The records don't name those departures as anything unusual. A doctor's note, a family relocation, a standard end-of-service form. And one retiree's retirement date, coincidentally, is the very day before the retention review began. A single date like that could be luck, so someone went back through the whole program roster and checked every name, every exit date, every signature on file across the full span of the mission. And the pattern repeats. 4 separate people, 4 separate exits, 4 years apart, each one landing within weeks of the same review cycle. Different job titles, different teams, no shared supervisor, nothing linking them on paper at all. But the timing lines up too well to be chaos. 4 retirements ahead of the same approaching deadline, spaced out so regularly that it reads less like coincidence and more like scheduling. 4 is not a coincidence, which leaves 5 words that no one in this story ever said out loud. Say them plainly, just once. The feature was already there. That's the sentence the NDA exists to keep unspoken, and it would resolve every contradiction in this story in a single breath. It explains the scrubbed frames, the withheld spectra, the retirements that all landed before the review. It says the anomaly wasn't camera noise or a stitching artifact. It was present in the raw data before anyone touched it, and it should not have been.
Then leave the sentence hanging where it lands, because the countdown is still running and the filter is still on. But before the countdown ends, there is one more place the feature might already be visible, a place no one ever thought to look.
So the check ran against an archive most people had forgotten. A ground-based observatory dataset from the 1980s captured a full decade before the mission ever left Earth. Its frames of Enceladus were taken at a resolution far too coarse to reveal the feature itself, maybe 30 kilometers per pixel at best, nothing that could resolve a crack.
But resolution was never what mattered here. What mattered was timing and the angle of the light. Because by the early 80s, telescopes on Earth were already catching the Moon at a specific solar geometry, morning at the Tiger Stripe region, low sun sweeping long shadows across fresh ice. A shadow in 1980s data would prove the feature has existed for 40 years, long before any avoidance could matter.
So the old frames got pulled and re-reduced, digitized, stacked, contrast stretched, until the noise floor showed through. They were hunting for something faint, a grazing shadow laid across that southern terrain at just the right solar elevation. One frame, almost an afterthought in the sequence, carried a distortion the others did not. It was not an obvious thing, more like a soft darkening that followed the ridgeline at an angle, hugging the slope of a sulcus, then thinning out where the surface opened flat. The geometry checked against the recorded solar azimuth, and the position matched the Tiger Stripe band to within the pixel scale of the era. A single old photograph is not a triangulation, not a second instrument confirming the first, but it does one very specific thing. Consistent is not proof, but it aligns the feature's birth date to before the modern era of this story entirely. And that changes how every decision reads. If the feature has been sitting in view since at least 1986, then nothing the mission did was accidental. Every flyby trajectory, every instrument pointing, every filter choice that happened to fall just short of the region now reads as a deliberate omission, not a scheduling gap.
A shadow cast in the 80s, a feature ignored by every camera that could have seen it. A countdown still running in parallel. Viewed forward from 1986, the whole observing campaign looks less like science and more like a story being steered, one careful step at a time.
And knowing decisions, 40 years long, require a single continuous thread of awareness, a thread that must run through the mission's very first proposal. Somewhere in the early 90s, a proposal went in for a Saturn mission, and its science section named Enceladus as a genuine target, not an afterthought. Buried inside that argument, in a single passing clause, was a phrase about a persistent surface irregularity. Read it at the time, and you would not look twice. A feature that stays put, across flyby after flyby, means something is holding it in place, and nothing in the era's models said that something should exist. Whether that clause was planted or simply honest, the proposal made it. The mission went forward. That clause was cited in exactly one later document, then vanished, and the citation trail ends at a name we have met once already. So we follow that single surviving citation. It passes through 3 intermediate papers, each one passing it along with growing hesitation, until it reaches its terminus, and the terminus is a name from an old margin note, the senior author on that 1986 chart.
The papers do not confirm the claim because they cannot. They point to it. They cite it as personal communication, which is a polite scientific way of saying this was told to someone directly and not committed to paper. Between the clause and the terminus, every paper avoids asserting it as its own finding, and none of them disagree with it either. They simply pass it on, like a sealed envelope nobody opens. A personal communication is not data, and it cannot be wrong in the same way a paper can, which makes it the perfect vehicle for a fact no one wanted to publish.
Here is what that citation form legally and scientifically permits. It allows an assertion without evidence, because the evidence sits only in a private exchange. It allows evidence without archive, because nobody filed the original. And it allows archive without review, because no referee ever read the underlying claim. Each step removes a layer of scrutiny, and each step also protects everyone involved, the cited, the citer, and the journals that let it through. That is the quiet utility of the form. It is how a field records something it does not want to defend, but also does not want to lose. So when a persistent surface irregularity enters the record as personal communication, it survives as rumor, weightless and untestable, exactly the status a dangerous idea wants.
And the one assertion it permitted, in this case, is precisely the one assertion that now looks true.
Line the pieces up in order, because the order is the argument, the shadow that fell where the geometry says it could not. The margin note in a hand that matched no signature on the report. The citation that led to a paper, then a different one, then nothing. The frames buried so deep, the camera was pointed the other way. Each of those was deniable on its own, by design. A shadow can be a trick of light. A margin note can be a bored technician. A buried frame can be bad film. But they do not all fail the same way. Taken together, they reduce to one assertion, and it is not the polite one. It is the one the field never printed, never defended, never managed to kill. That Enceladus was not always the moon we see now. That its surface was partly made before any probe got there. That the anomaly has a history, and the history predates us. Claims, however, are not conclusions, and the data that would turn this claim into a conclusion still sits in the last sealed archive on Earth. Deep in a university basement sits a microfilm archive that was never digitized. The scanner budget ran out in 1974, and no one asked again. It holds the pre-spaceflight models drawn before any probe returned a single image of those worlds, including the Enceladus models from the early 1960s. In their day, this was the modern way to save everything, when paper had grown too heavy to keep. One reel among them is the one this entire trail has been circling, and on that reel, in red ink, a stamp that has survived every director, every merger, every format upgrade since, not for reproduction. The clerks who catalogued it are gone. The instruction is not. 60 years of clerks who never touched it. 60 years of graduate students waved away with a signature and a shrug. The note has outlasted the institution that issued it, and it is still sitting there, doing exactly the job it was written to do. The stamp is handwritten, and handwritten stamps expire under the retention law that just released everything else. The retention law has a number, and that number has now passed. When the statute lapses, a restricted record becomes ordinary paper. The reel is copyable today, legally, for the first time in 60 years. The procedure is boring, which is how you know it is real. A request in writing, a reference checked against the index, a signature on the reading log. Then the reel comes out of the drawer and goes into a reader, and who sits at that reader matters, because the person has to know what the frames claim before the bulb even warms. The read itself is straightforward, frame by frame, exposed for the first time onto modern eyes. Then the testing begins. The 30-year-old shadow data is recovered, and the early 1960s elevations are laid over it. The comparison is nothing more than geometry, feature matched against feature. Do the two descriptions of the same world line up? The first read of that reel happens off-camera, in a university basement, in the early hours of the morning. The reel spins down, and the comparison sits there, quiet and complete. The 1960s model carries the same irregularity, the same off-center bulge, drawn a full 20 years before the survey that supposedly found it. Same shape, same position, same stubborn presence on the map. Not a measurement repeated, but a drawing made decades earlier, in a decade when no instrument had ever reached that world. Every theory the modern story built on that feature collapses in one frame. It could not have been discovered by the flyby if it was already on paper before the flyby was a possibility. A drawn irregularity is not a measurement, it is a prior belief, and prior beliefs are the last thing standing.
That brings us to the hardest question this material raises, and it cannot be waved away. Could the feature exist on that chart because someone believed it existed there?
Not as a fraud, not as a mistake. Belief, in this archive, behaves exactly like evidence. It gets written down, it gets cited, it gets carried forward, and once it is written, it is indistinguishable from fact.
A confident line on a map survives longer than any photograph. Photographs age, charts are copied, and each copy is a small act of faith from the person tracing it.
And if belief is the mechanism, then the answer to this entire story was written before any instrument flew.
The last page of the 1960s model closes the loop in a way nothing else could. Beside that hand-drawn irregularity is a label, written in careful French in lowercase letters.
Not a number, not a note for the draftsman, a term that appears nowhere else in the entire literature, on any chart, in any paper, before or since. Thermal refuge, a place in the cold where warmth survives, drawn by someone who never saw the world, 40 years ahead of the instruments that would hunt for it. Thermal refuge, a place in the cold where warmth survives, is the one name this entire story kept circling and never once used.
So set the picture right. This was never a forgery, and nobody was hiding the truth from you. It was a quiet fact, sitting in the open, protected by how hard it is to look at an icy world and know what warmth you're actually seeing.
Enceladus spends its entire history being read at a distance, through glare and noise and the limits of old instruments. A warm pocket in a body that cold doesn't announce itself. It sits below the surface, stable, patient, shielded by every mile of frozen water above it. And the people who kept circling it, generation after generation, never had the tool that could prove what they suspected. So the refuge stayed a refuge, not because anyone closed it off, but because the world had always guarded its own quiet corner. And protected places, on worlds like this, are exactly where the question of life has always been allowed to hide. Because that's what a warm pocket under an icy shell really is. It is the one ingredient habitability refuses to do without: liquid water, kept warm by the world itself, sealed off from the vacuum above.
The subsurface ocean of Enceladus was confirmed in 2014 by Cassini's gravity data, and plumes of vapor were found venting through the south polar cracks as far back as 2005. But a stable warm pocket, sitting in one place for decades, is a different promise. It means chemistry has had time.
Chemistry had time to mix, to react, to build the kinds of molecules that need a sheltered spot to survive. For the instruments that would land there, it turns a frozen moon into something almost familiar. And admitting it was always there, is the hardest part. It means the search didn't begin with the mission. It began 40 years earlier, with a hand that never touched the surface. The next mission's landing site, as it happens, was chosen by planners who never saw these frames. Planners working from gravity maps, from surface temperature readings, from decades of published charts. They studied where the ice was thinnest, where cracks suggested upwelling warmth, where the math said a stable pocket might sit, and then they picked a site, unaware of the older trail. The frames that the refuge appears in map directly onto that chosen ground. The committee made its decision from newer data, and the older data, by pure chance, agrees with it exactly. Two independent routes, 40 years apart, landing on the same patch of ice. That is not a coincidence you build by faking a chart. It is a coincidence you can only inherit. The geometry did the work that the conversation couldn't. Which means the mission may stumble onto the answer by pure geometry, no matter who wanted to avoid it. The trajectory doesn't aim at the moon's face at random. It threads a narrow corridor, one engineered to cross the footprint that model keeps drawing on the south polar terrain, a patch of ground no probe has ever flown over before. For a few minutes, the spacecraft skims low, close enough that its heat-mapping instrument can resolve warm pockets smaller than a city block. If that plume source is really sitting there, the sensor sees it as a bright red smudge against the blue-white shell of ice. A single overflight can settle decades of argument, and that is why the timing matters more than the trajectory does. The very first pass is scheduled for a date, and that date is worth saying out loud. Call it in your calendar, because it is closer than you think. The first overflight happens in 2031, 10 short years from now, a window that slips by fast in the lifetime of a spacecraft or a planet. Now set that date beside another. The retention clock, the one keeping whatever the sealed archive is holding, unlocks in 2037, with 2042 as the final release. Same decade, two doors. The spaceship takes its readings just as the vault doors finally swing open. One world, one decade, and the data arriving from two opposite directions at once. Two doors, one world, and the entire question of what else hides under an icy ocean arriving at once. Between now and that first flyby, the wait is not silence. The orbital models get refined every time a telescope catches the plume flickering, and each observation narrows the map of where the overflight should look. The community is already rehearsing the questions. What temperature would prove the warm pocket is real? What chemistry in a single plume sample would rewrite our ideas about where life can begin, and which molecules would settle it in one gasp? Every instrument team is stacking the priority list now, knowing they get one clean shot at this terrain in the decade. One of those questions is a question no mission has ever been able to ask about any ocean in the solar system. Every proposal document lists the instruments, the orbit, the budget line items, and every proposal document, if you read closely enough, is really asking the same old question: does liquid water have biology in it? That's a question we already know how to ask. The new one isn't written anywhere. It lives in the gap between the mapped ocean and the warm pocket, between what the radar sees and what a single overflight of one narrow fissure could finally settle. Not whether life can exist in an ocean, whether life can exist in a place the ocean forgot to reach, a sealed chamber kept warm by nothing but the planet's own stubborn heat. That's the mission's real payload, and no engineer on the team has to say it out loud. They all know. The instruments are built for it, the landing site was chosen for it, the whole decade of waiting is pointed at it. The answer will take a decade, but the asking is already over. So picture the overflight, years from now. The spacecraft drops low, the plume passes through the mass spectrometer a few hundred kilometers up, and the data arcs back to Earth over a stretch of nights. Then come the months of calibration, the arguments over background noise, the first cautious abstract. The first paper will land quietly. Some Tuesday morning, a preprint, a press release, a headline about a molecule nobody expected. And 50 years late, a public waking up to the fact that this feature had been sitting in plain sight the whole time, never hidden, never secret, just unlooked at. By then, the people who first flagged it will be older, some of them gone. The shadow on the film, the margin note in a routing error's wake, the spool nobody rewound, all of it grinding slowly into a thing they could have seen at any moment and simply chose not to. When that first paper drops, someone will have to tell the story of how they found it, and someone else will have to explain why it took so long to look. Rewind it all once more then. A telemetry packet routed to the wrong desk. A technician's margin scrawl. Check this. A shadow on one frame of 60-year-old film that a reviewer dismissed as a scratch. A basement reel, marked, shelved, and never rewound. Every step was a human choice. A person deciding the shape was worth a second glance or deciding it wasn't. The images were always there. The evidence never changed, never degraded, never ran out. Only attention did. And that's the part the missions can't fix. No spacecraft can be built to care. The real question isn't what's under the ocean, it's who decided, and for 60 years, that we didn't need to look. Not one person set out to hide a moon. Every engineer was just wiring a solar panel, filling out a power budget, picking a filter that fit the schedule. Each choice was reasonable, defensible, the kind you'd sign off on without a second thought. That's what makes it worse. No villain waved a hand, no order was given. 60 years of perfectly innocent decisions, each nudging the next spacecraft toward the warm pocket and past it, all of them adding up to a habit no one agreed to and no one noticed forming. And the countdown never paused for politeness. While committees met and budgets got trimmed, Enceladus kept venting 200 kilograms of water every second into space, waiting. The last camera that looked at cold worlds is already on its way back to the archive, and the next one is already being built with the warm pocket already marked on its chart. Because here's what changed in those 60 years. The mark is made now, and marks don't get erased. Every proposal written from this day forward carries those coordinates in its noise, its margins, its unspoken assumptions, whether the mission formally admits to them or not. That knowledge lives in hundreds of people who weren't even born when the first pictures came back. They can't unsee the fracture, can't unlearn the temperature reading, can't pretend they don't know the water's still flowing. The community holds it now, and no archive filing can take it back. The geysers don't shoot straight up. Cassini's imaging team measured the plume angles in 2008 and found they tilt between 15 and 30 degrees west, always away from the sub-Saturn point. That's the spot on Enceladus that constantly faces Saturn, like the moon's near side to Earth. The tilt means the ice shell rotates faster than the core, an effect called non-synchronous rotation. The measured lag is small, about 0.12 degrees per day, but over a million years it adds up. The tiger stripes drift west relative to the gravitational stress field. The hottest vents today sit where the ice is being pulled apart the hardest, not where they started. It's a slow-motion grind, and the heat follows the crack as it moves. The plume's particle size distribution peaks at 2 microns. That's the size of bacteria, purely by coincidence, but it matters for a different reason. Particles that small stay aloft long enough to escape Enceladus's gravity entirely. The moon's escape velocity is only 239 meters per second, and the geysers launch ice grains at speeds up to 400 meters per second. So every eruption seeds Saturn's E-ring with fresh material. The ring is 180,000 kilometers wide, but only 2,000 kilometers thick, a ribbon of ice stretching from Mimas to Titan. Enceladus orbits right through the densest part. Before Cassini, no one knew where the E-ring came from. Now we know it's Enceladus exhaust, replenished in real time. The mass loss rate is 200 kilograms per second. That's not much for a moon, but it's relentless. Over the age of the solar system, Enceladus would have lost 30 trillion tons through the geysers. That's 0.03% of the moon's total mass, enough to fill the ocean 10 times over. Either the geysers are young, or the ocean is constantly being refilled from below. The temperature gradient is wrong. The South Pole vents measure 180 to 190 Kelvin, but the surrounding terrain sits at 70 Kelvin. There's no smooth transition, no heat halo spreading out. It's a sharp boundary, like someone drew a line at 55 degrees south latitude and turned the heat on below it. The energy budget doesn't close either. The south polar terrain radiates 15.8 gigawatts, more than double what tidal heating models predicted for the whole moon. Enceladus is 500 kilometers across, smaller than Arizona. Squeezing that much power out of tidal flexing requires either a thinner ice shell than observation support, or a heat source no one's accounted for.
The salinity reading came from the E-ring dust. When Cassini's cosmic dust analyzer flew through the plume in 2008, it tasted sodium chloride, potassium chloride, and sodium bicarbonate. The sodium to potassium ratio matched Earth's oceans almost exactly, about 26:1. That ratio only happens when water has sat in contact with rock for a long time.
The silica particles were even stranger. They measured 6 to 9 nanometers across, far too small to form in cold water. Lab experiments show that silica grains that size only crystallize above 90 degrees Celsius. The ocean floor must have hydrothermal vents, hot enough to dissolve rock and precipitate it back out as nanoparticles. The hydrogen measurement took 3 years to confirm. Cassini's ion and neutral mass spectrometer detected molecular hydrogen at 0.4 to 1.4% by volume in the plume. Hydrogen doesn't last long in water. It reacts, it escapes, it gets consumed. Finding it in the plume means it's being produced continuously, right now, somewhere below. The only known process that makes that much hydrogen is serpentinization. Hot water reacts with olivine and pyroxene, the minerals in Earth's mantle, and splits water molecules apart. The oxygen binds to the rock, forming serpentine. The hydrogen bubbles up. On Earth, serpentinization powers ecosystems at mid-ocean ridges, feeding bacteria that live without sunlight. The calorie count is 300 terajoules per year, the energy available from hydrogen alone. That's enough to support 30,000 tons of biomass, assuming Earth-like efficiency. For comparison, a single hydrothermal vent field on Earth supports about 10 tons. Enceladus's ocean could theoretically feed a biosphere 3,000 times larger than a single vent, if anything's there to eat. The ice shell thickness is debated. Gravity data suggests 20 to 25 kilometers globally, but the South Pole could be much thinner. The plume vents erupt from fractures that reach the ocean in under 5 kilometers mimes. That's thin enough for tidal pumping to drive water directly to the surface, no pressurized reservoir needed. The fracture spacing is oddly regular. The 4 main tiger stripes are spaced about 35 kilometers apart, running parallel for 130 kilometers each. Computer models show that spacing matches the wavelength of a tidally driven crack propagating through ice. It's the same physics that cracks frozen lakes on Earth, but scaled up and powered by Saturn's gravity. The wobble Cassini measured is called libration. Enceladus rocks back and forth in its orbit by 0.120 degrees, twice per orbit. That's 4 times larger than it should be if the moon were solid all the way through. The extra wobble means something's decoupled inside. The ice shell floats on liquid, sloshing slightly as the moon speeds up and slows down in its elliptical orbit. The ocean depth is at least 10 kilometers, possibly deeper. Gravity data can't distinguish between a 10 kilometers ocean and a 30 kilometers ocean if the density is the same. But the sloshing amplitude limits how thick the ice can be. If the shell were more than 30 kilometers thick, the libration would dampen out. The ocean has to be thick enough to let the shell slide freely. The orbital resonance with Dione is the key. Enceladus orbits Saturn twice for every 1 orbit Dione completes. That 2-to-1 resonance locks Enceladus into an elliptical orbit, forcing it closer and farther from Saturn every 33 hours. The changing distance flexes the moon like a rubber ball, generating heat through friction. But the resonance is fragile. If Enceladus loses too much mass through the plume, its orbit will drift and the resonance will break. Calculations show the current eruption rate can only last another 10 to 30 million years before the orbit circularizes. After that, Tidal heating drops by 90%, the ocean freezes, and the geysers die. The plume's variability was a surprise. Cassini watched the eruption rate double and halve over the course of a single orbit. The plumes peak when Enceladus is farthest from Saturn, at apoapse, when the tidal pull is weakest. That's backwards from what you'd expect. The stress is highest at periapse, closest approach, but the vents shut down there. The explanation is tidal gating. When Enceladus swings close to Saturn, the tidal squeeze clamps the fractures shut, pinching off the water supply. At apoapse, the pressure relaxes, the cracks open, and water surges up. It's like a slow-motion valve, opening and closing twice per orbit, driven purely by Saturn's gravity. The radiation environment is brutal. Enceladus orbits inside Saturn's magnetosphere, where charged particles spiral along magnetic field lines. The radiation dose at the surface is 0.002 grays per day, low by Europa standards, but enough to break down organic molecules over time. Anything living on the surface would need thick ice shielding or fast repair mechanisms. But the ocean is shielded. 20 kilometers of ice blocks nearly all radiation. The ocean floor, where hydrothermal vents would be, is as radiation-free as Earth's deep sea. If life exists on Enceladus, it's not on the surface. It's in the dark, kilometers below, clustered around vents we'll never photograph.
The mission proposals started arriving in 2010. The first was called the Enceladus Life Finder, a $425 million probe designed to fly through the plume 50 times and analyze its chemistry in detail. It carried a mass spectrometer 10 times more sensitive than Cassini's, capable of detecting amino acids, lipids, and complex organics.
It didn't get funded. NASA's review panel ranked it highly, but said the technology wasn't mature enough. The mission needed a landing system that could survive the plume's ice grains at high speed, and a sample collection mechanism that wouldn't contaminate the instruments. Both were prototypes, not flight-proven hardware. The second proposal was cheaper, a $185 million orbiter called Enceladus Life Signatures and Habitability. It would orbit Enceladus at 50 kilometers altitude, low enough to skim the plume's outer edge 20 times. The trade-off was lower sample density. At that altitude, the plume thins to 1 particle per cubic meter. Cassini sampled 10,000 particles per cubic meter by diving closer. That proposal didn't fly either. The launch window closed in 2018, and the funding went to a Mars rover instead. The rover was already in development, lower risk, and Mars was the flagship priority. Enceladus got bumped to the next decade.
The third proposal was the most ambitious, a dual spacecraft mission called Enceladus Orbiter and Impactor, costing $780 million. One spacecraft would orbit at 25 kilometers and sample the plume. The other would deliberately crash into the South Pole at 5 kilometers per second, excavating subsurface ice and launching it into the plume for the orbiter to analyze.
The impact would dig a crater 50 meters wide, exposing ice from 10 meters below the surface. That ice would be older, less processed by radiation, potentially richer in organics. The orbiter would fly through the debris cloud 10 minutes after impact, collecting fresh samples before they dispersed. But the proposal violated planetary protection rules. Crashing a spacecraft into Enceladus counts as harmful contamination unless the spacecraft is sterilized to the same standard as a Mars lander. That requires baking the entire probe at 110 degrees Celsius for 50 hours. Electronics don't survive that. The mission would have needed a completely new spacecraft design, adding $200 million to the cost. So the team proposed an alternative: crash the impactor into the North Pole instead, where there's no plume and no obvious ocean access. The debris would still reach the South Pole via Enceladus's thin atmosphere, carried by wind over 6 months. The orbiter would sample the settled dust later, after it had migrated. That idea got rejected too. The review board said the contamination risk was still too high and the science return was too uncertain. Crashing into the North Pole might excavate ocean water if the ocean is global, which some models predict. If it is, the mission would contaminate the ocean anyway. If it's not, the mission wouldn't sample ocean material at all. Either way, the gamble was too big. The cheapest option on the table now is a Europa Clipper piggyback. Clipper launches in 2024 and will loop through the Saturn system for a gravity assist. The trajectory takes it within 1 million kilometers of Enceladus in 2030, close enough to photograph the plume at high resolution, but too far to sample it. It's a consolation prize, not a mission. The real mission everyone wants is a lander. Land on the south polar terrain, drill through 100 meters of ice, and lower a probe into the fracture. Sample the water directly, not the plume. Bring it back to the surface, analyze it on site, and transmit the results home. Price tag is $2.08 billion, assuming no delays. The engineering problems are solvable but expensive. The lander needs radioisotope heaters to stay warm in 70 Kelvin temperatures, a drill that can bite into ice without overheating, and a winch strong enough to lower a 50 kilograms probe on a tether. It also needs to avoid the active vents, which erupt without warning and could coat the lander in ice. The landing site selection is a nightmare. The south polar terrain is only 5% of Enceladus's surface, and most of it is too rough to land on. The tiger stripes are gouged with ridges 200 meters tall and trenches 500 meters deep. A lander needs flat ground within 10 kilometers of an active fracture, and there are maybe 5 candidate sites total. The drill depth is the real bottleneck. Lab tests show that drilling through Enceladus-style ice takes 2 watts of power per meter per hour. Drilling 100 meters would take 200 watt-hours, or 8 days of continuous operation on a 1-watt budget. A lander's radioisotope generator puts out 100 watts, but most of that goes to heating and electronics. The drill gets maybe 5 watts. So the mission would take 40 days just to reach liquid water. That's 40 days sitting on the surface, hoping the lander doesn't tip over, hoping the drill doesn't jam, hoping a geyser doesn't erupt underneath it. Every hour adds risk. The baseline plan assumes 60 days total surface time, with 20 days of margin for setbacks. The sample return is the biggest unknown. Once the probe reaches liquid water, it has to collect a sample, seal it, and pull it back up without freezing. Water at 270 Kelvin will freeze solid in 10 seconds if exposed to vacuum at 70 Kelvin. The probe needs insulation, a heated chamber, and a way to keep the sample liquid during the 40-day ascent. One solution is to add antifreeze. Mix the sample with methanol or ethylene glycol, dropping the freezing point to 200 Kelvin. But that contaminates the sample chemically, making it harder to detect organic molecules. The alternative is active heating, but that drains power and adds weight. Either way, the mission gets more complicated and more expensive. The contamination calculus goes both ways. We worry about contaminating Enceladus with Earth bacteria, but we also worry about contaminating Earth with Enceladus bacteria, if any exists. A sample return mission would have to land in a contained facility, open the sample in a biosafety cabinet, and sterilize everything before release. That's never been done for an icy moon sample. The political problem is worse than the technical one. Enceladus competes for funding with Mars, Europa, Titan, Venus, and a dozen asteroid missions. Mars has 50 years of advocacy and a lobbying base. Europa has congressional champions who wrote it into law. Enceladus has compelling science, but no constituency, no long-term commitment, no flagship mission on the books. The Decadal Survey ranks missions every 10 years. The 2023 survey listed an Enceladus orbiter as a high priority, but not the top priority. That spot went to a Uranus probe. Enceladus is second tier, meaning it might fly in the 2040s if the budget allows. By then, Cassini's data will be 35 years old. The archive problem is getting worse. Cassini collected 635 gigabytes of data, stored on hard drives at the Planetary Data System. The drives are backed up, but the software to read the data is not. The file formats are proprietary, written in 2004, and the engineers who wrote them have retired. In 20 years, no one will remember how to pass the raw instrument telemetry. There's a project underway to convert everything to modern formats, but it's underfunded and understaffed. 2 programmers working part-time, converting 200 gigabytes per year. At that rate, the archive won't be fully converted until 2027. If funding cuts in, the project will stall, and chunks of Cassini's data will become unreadable fossils. The same thing happened to Voyager. Some of Voyager 2's Neptune images were stored on magnetic tapes that degraded before anyone copied them. The data still exists physically, but the error correction codes failed. 15 images are corrupted beyond recovery. We flew past Neptune once, and we lost pictures because no one paid to maintain the archive. Enceladus won't wait for us. The geysers are eroding the fractures, widening them by millimeters per year. In 10,000 years, the tiger stripes will migrate 5 kilometers west, and the current hotspots will shut down. In 1 million years, the orbital resonance with Dione will drift. Tidal heating will drop, and the ocean might freeze. We're seeing Enceladus in a geologically brief active phase. The window to study it is maybe 100 years, the span of human spaceflight capability. Cassini gave us 13 of those years. We've used 15 more writing proposals and waiting for funding. That leaves 70 years, maybe 3 more missions if we're lucky, before the technology or the political will runs out. After that, Enceladus becomes a historical footnote, a place we studied once and never went back to. The science return per dollar is hard to beat. Cassini cost $3.02 billions and rewrote planetary science. An Enceladus orbiter would cost $800 millions and could answer the life question directly. That's 4 times cheaper than Europa Clipper and targets a more accessible ocean. But it's not Mars, so it sits in the queue. The public doesn't know Enceladus exists. Mars rovers get press conferences and Twitter accounts. Europa gets magazine covers and documentaries. Enceladus gets a footnote in Cassini retrospectives, if that. There's no constituency demanding an Enceladus mission because no one outside planetary science has heard of it. That's starting to change. A 2021 poll by the Planetary Society found that 23% of respondents could name Enceladus when asked about icy moons. That's up from 4% in 2015. The number is still tiny, but it's growing. Every documentary that mentions the plume, every article that explains the hydrogen, builds the case for going back. The advocacy is working slowly. The 2023 Decadal survey mentioned Enceladus 47 times, up from 12 in 2013. The Europa Clipper authorization bill includes language directing NASA to study an Enceladus mission for the 2030s. It's not a commitment, just a study, but it's progress. Congress is starting to notice. The international interest is stronger. The European Space Agency proposed an Enceladus lander in 2019, a joint mission with Japan called the Enceladus Life Investigation. It would launch in 2038, land in 2050, and drill for 90 days. The price tag is 1.2 billion euros, split between ESA and JAXA. It's still in early planning, not yet approved, but it's farther along than any NASA concept. China is watching too. The China National Space Administration published a white paper in 2022 listing Enceladus as a target for the 2040s. No details yet, just an acknowledgement that it's on the radar. If China flies an Enceladus mission before NASA does, it'll be the second time they beat us to a major solar system destination, after the moon's far side. The competition might be what it takes. The political argument for an Enceladus mission gets stronger if someone else is planning one. Letting another country answer the life question first would be a symbolic defeat, the kind that moves congressional budgets. It's not the best reason to go, but it's a reason that works. So the camera returns, and the next one launches carrying the old question with it. Not whether something hides under that ice, But how long a species that knew where to look can call itself innocent of it? The mark was always the answer. We just weren't ready to read it. Subscribe to see where the pointing finally lands.